Good day, Earth scientists. Hopefully you're in a comfortable place where you're listening to this presentation and a new introduction of a digital learning platform that we'll be using more of in the future. Please have a copy of your Earth Science reference tables with you while you view this presentation. You should have the copy of the reference tables open to page 7. And at the end of this PowerPoint presentation, we will be using the Metamorphic rock ID table at the bottom of page 7 to work through a couple of problems. So today's lesson is on metamorphic rocks, and this is an introduction for you. We'll tackle the topic in more detail in class tomorrow. If you think about the word metamorphosis, you may have heard this in regards to the natural world before. If you think about a caterpillar metamorphosizing into a butterfly, it's changing its form. And we're going to look at metamorphic rocks as any rock which has been changed from its present form to a new structure. We can categorize metamorphism into two types, either regional or contact. Let's look at regional metamorphism first. Regional metamorphism is caused by exposing rocks to extreme pressure and heat. This extreme pressure and heat causes them to change their current structure into something different, creating a new metamorphic rock. Regional metamorphism happens over wide regions. That is a widespread area that could be up to 1,000 kilometers in distance. Here's a nice diagram of regional metamorphism in action. We have two tectonic plates that are colliding here and creating an episode of mountain building. You can see by the two arrows that are converging that there is an extreme amount of pressure being put on the crustal material here. This extreme pressure causes deformation, that is change in the structure of the rock, uplift, and a widespread area of regional metamorphism. You can see by the squiggly lines that the structure of the rock is being compressed and changed. The second type of metamorphism is contact metamorphism. Contact metamorphism occurs when hot, molten magma contacts an existing bedrock structure. This could be a structure of sedimentary rocks, igneous rocks, or a structure of metamorphic rocks that are going to be further metamorphosized. Remember, hot molten magma is a source of extreme heat, and this heat is responsible for changing the crystalline structure of the existing rock. This is a cross-section view of an igneous intrusion and extrusion represented by A. You can see by the dark hatch marks that every place this molten material touches rock, that rock will be metamorphosized. This is a very typical Regents level diagram showing contact metamorphism. Metamorphic rocks will often have foliation or a distorted structure. These will be the physical characteristics that will enable us to spot a metamorphic rock. Let's talk about distorted structure first. In this example, you see a piece of banded gneiss. You can see that the band of quartz has been bent and twisted. This is a prime example of a distorted crystal structure. And when you see this, you know you're looking at a metamorphic rock. This is another picture of a distorted layered rock. In this case, it's a piece of foliated phyllite. And it's easy again to see the distortion in the layers. You want to think to yourself, what type of forces could create this enormous amount of pressure that would actually distort the rock structure and deform it? Foliation is a grain to the rock, and it will often exhibit itself as a layer of aligned minerals. There are several different types of foliation. There's a gneissic foliation, where the minerals have been squished into separate bands. Here you see quartz crystals in their original structure within an igneous rock. such as granite. We've applied a whole lot of pressure across the rock here, as you would see in a plate tectonic collision, and watch what happens to the quartz crystals. So we've now flattened and squished them, and as we do that, they will create bands, or what we like to call zebra stripes. If you see a rock with banding or zebra stripes, it is a telltale sign that you're looking at a piece of gneiss, which is a metamorphic rock. There's a very nice picture of a piece of banded gneiss. You can see the quartz arranged into separate bands within the overall structure. The second way that metamorphic rocks can appear is in a layering. Layering would be a complete separation among the crystalline structure as opposed to banding. You can see there is a total separation of minerals. This is an example of a piece of schist with separate layers. The cause of this layering effect are the actual minerals being aligned into parallel planes. This schistose foliation, as I already mentioned, is the minerals being squished together and often presents itself in the form of flaky mica. If you remember mica from our mineral ID, it's very shiny, it has exhibits cleavage, and it breaks along one plane. There's a piece of schist. You can see the very shiny mica crystals. And here is the world famous holy schist. Third type of foliation is a slaty foliation. This is where the rocks split into flat, thin layers. Normally occurs in the presence of only mica crystals, such as are found in clay. And here's a very nice picture of slate. You can see the mineral alignment in the layers. These layers will split very easily along the alignment plane. Slate comes from the metamorphosis of the sedimentary rock shale. And as we've mentioned before, many of the rooftops that you can see from our classroom here in Schenectady have beautiful slate roofs. Okay, please make sure you have your Earth Science reference tables in front of you. We're going to do a couple of progressions of metamorphosis with the table at your fingertips so you can follow along. Once again, the reference table page is 7, and we're looking at the scheme for metamorphic rock ID at the bottom of the page. So, if you look at the top of the table, you'll notice the rock, metamorphic rock slate, and watch what happens as we apply heat and pressure. Slate will metamorphosize into phyllite, the rock phyllite. All right, let's try another one. If we start this time with a piece of phyllite and we add, that's right, heat and pressure, heat and pressure, phyllite will metamorphosize into schist. This time if we start with schist, and I think you see the pattern by now, and we add further heat and pressure, we will create the new metamorphic rock, gneiss. I hope you've enjoyed this initial presentation on metamorphic rocks, and I'll look forward to helping you apply your new understanding in class over the next several days. Thank you.